In the center of the universe, where the moon cannot escape, there is one of the most mysterious and terrifying creatures known to man. Dark, small, and of unknown mass, these titans of the universe have fascinated scientists and captured imaginations for generations. Today, renowned astrophysicist Neil deGrasse Tyson is on the sidelines of the exhibition, uncovering the mysteries of black holes. Get ready for an interstellar journey that will challenge your understanding of the universe and reveal secrets that could change our understanding of the universe. Boy, it's dark, and there's a lot in it. And it's small. There are 3 guns in the place that point to a very dangerous prison. The place can be scary. The dangers lurking in the great room can be terrifying. While this is true of the entire subject of space exploration, the most fascinating and feared area is black holes. These powerful animals are the subject of many research projects around the world. Scientists have been trying to find out what black holes are and what they contain. But all this is changing now. Neil deGrasse Tyson revealed something important. Our black hole is smaller than the black hole at the center of the Andromeda Galaxy, our nearest giant galaxy. So, do we envy black holes? I think we are doing it. We finally see what's inside a black hole, and it just makes you feel worse. So join us as we take you on this intergalactic journey and answer one of history's most famous questions. What is a black hole? The mass of a black hole, created from a massive explosion, squeezes into a very small space, creating a vacuum so strong that nothing, not even light, can escape. When something is in there, it stays there forever. These powerful forces range in size from interstellar black holes, many times the mass of the Sun, to massive forces at the center of galaxies, millions or billions of our mass. Today, scientists have been observing the effects of black holes for decades, and with each piece of data we uncover, hundreds of mysteries are revealed. While they may look big and powerful, they may not have a main message. They do. Black holes don't just exist in space. It's made up. To be born, they need the remnants of massive stars that have run out of their nuclear fuel. These stars undergo supernova explosions, a spectacular event that marks the end of their lives. During a supernova, the outer layers of the star are thrown into space as the core collapses. Not all collapses are equal. If the core has several times the mass of our Sun, the gravitational force will overwhelm all other forces and the core will collapse inward. This collapse is so powerful that it compresses matter into a very small ribbon, creating an object with a magnetic field so strong that nothing escapes its gun, creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, the known type, vary in mass from several to 10 times the mass of the Sun. At the core of a black hole is the singularity, a region of infinite density and curvature of space. According to our current understanding of physics, the laws of nature break down at this point, and our theories cannot fully explain what happens in isolation. To really understand what special things look like, we need to think outside the box in physics. A discrete point refers to a point in space where certain quantities are unbounded. These singularities occur in various theoretical contexts, such as the beginning of the general universe, known as the Big Bang singularity, and in black holes. A major challenge arises when we study the Big Bang singularity. According to this theory, the universe originated from a hot and very blue state about 13.8 billion years ago. But when we go back in time to this first situation, the equations of general relations, which govern the behavior of the sex, break down. This distinction shows that our current understanding of physics cannot fully describe the conditions during the Big Bang. Solving this problem requires a theory that combines general relativity and principles of quantum mechanics. A black hole is a special object in the core. These are places where gravity is very strong and spacetime is very distorted. According to general relativity, matter and energy falling into a black hole will reach its singularity and compress infinitely. This concept is beyond our current understanding of physics. In addition to this problem, the challenge of individuality has encouraged researchers to search for the theory of gravity, which seeks to combine the principles of general relativity and quantum mechanics. Quantum gravity aims to provide a framework for explaining the behavior of space on temporal and microscopic scales. Such a theory can explain the nature of particular things and the functioning of the world point. One of the ways to do the special thing is the ring gravity theory. This theory suggests that space exists on very small measurable scales, meaning that it exists in discrete and discrete units. These basic units are called rings or thread networks. In quantum gravity, the concept of measurement is related to space. This means that space is not considered a fixed and infinite entity, but rather a collection of discrete elements. These discrete units of space are called interconnected loops or networks that represent the underlying structure of the Earth's fabric. In the framework of the ring's gravity, it is possible to determine the various anomalies associated with black holes and supermassive explosions. One of the main insights of this theory is that on very small scales, the discrete nature of space precludes infinite density and curvature leading to singularity. For example, in classical relativity, in the context of black holes, quantum gravity shows that as matter collapses into the core, the spacetime layer shrinks. This size prevents the substance from reaching absolute specificity. Instead, the collapsing object encounters a large bump near the nucleus, recoils, and begins to grow again. This phenomenon leads to the formation of a new region of space inside the black hole, called a supermassive black hole or jump region. Stellar black holes are the most common type of black hole in the universe. It occurs as a result of the collapse of the barrier at the end of the life of a large star. When a supermassive star has used up all its nuclear fuel, the outward pressure created by nuclear reactions can't stop the gravitational pull pulling it inward. The loosening becomes so strong that the star collapses under its own weight. This collapse creates a stellar black hole. When a star collapses, it becomes very compressed, packing a lot of mass into a very small volume. As a result, stellar black holes have up to 20 times the mass of the Sun. Despite their mass, their size is very small. Their diameter is only a few kilometers, which shows how thick they are. The very high density of a stellar black hole creates an event boundary, a region beyond which nothing, even light, can escape. The point of no return represents the point of no return, where the pull of the black hole becomes so strong that everything and information that comes out of the black hole remains forever. Then there are intermediate mass black holes. Although the mass range of intermediate mass black holes remains for scientists to study and refine, they are believed to be thousands to tens of thousands of times the mass of the Sun. These giant animals inhabit the regions of most galaxies, including our own Milky Way. They have a strong influence on their galactic environment and have a significant impact on the evolution of galaxies. The formation of supermassive black holes is a poorly understood area of research, but even then, many different theories have been put forward to explain its origin. A popular theory says that supermassive black holes grow from smaller ones through a process called accretion. According to this theory, matter such as gas, dust, and stars gather into a black hole, forming a rotating disk called an accretion disk. The black hole's gravitational pull pulls material from this disk, swirling it inward and merging with the black hole. Over time, this constant accretion of matter causes the black hole to grow to a very large scale. During the accretion process, a large amount of energy is released as matter falls into a black hole. With this power, some of the brightest and most powerful signals in the world were transmitted. But far from all of these are black holes, which represent a mysterious type of black hole characterized by the existence of an electric charge. There are two main types of charged black holes: Reissner-Nordström black holes and Kerr-Newman black holes. Each type exhibits unique properties that result from the interaction between the black hole's charge and other factors such as spin. Reissner-Nordström black holes charge but do not rotate. It is described by the Reissner-Nordström solution in the framework of general relativity. The price of these black holes affects the behavior of their platform. However, in terms of overall structure, Reissner-Nordström black holes are similar to free black holes.